some way I'm very happy to be here in Ukraine. It has been a fantastic meeting, most important meeting you all, and to be able to be here and dream together about a future together that we can make the citizens of Ukraine better, and sharing our knowledge and learning from you. Today I'm not going to talk. I think that I tried to do a video myself to tell you what are we doing, but I tell you, YouTube is a wonderful thing. There are people that presented very eloquently the subject that we want to do today. So without much ado, let's start our first video. And it's about the dreams that we have in the future, that we don't have to have shortness of organs. And making that is about how can we develop. Do we have sound? Can we use my computer and not put the sound?
Return them to life. Yeah. But instead of giant green monsters, these researchers are creating hearts, lungs, limbs, and kidneys that can one day be used to replace failing organs in people. Reporting in Nature Medicine, Harold Ott and his team described their vision of the future and how they created a functional, transplantable kidney in rats.
What we try to do here is to regenerate organs for transplantation, organs for patients with end-stage organ failure.
Using donor organs that would not normally be suitable for transplantation, Ott's team reanimates them by first washing away native cells with a soapy solution. What's left behind is a natural scaffold of structural proteins that can be repopulated with stem cells taken from a patient.
What's fascinating is that you're able to, with that process, preserve the blueprint of the organ, but it's completely washed empty. It's a mere a shadow of the original tissue. Now the major hurdle here was to get the cells, the viable building blocks, back into the right spots within that organ. That we did through creating literally a pressure gradient across the kidneys, so we're able to suck these cells into the tissue, into the kidneys, into the right spots.
The organs were placed into chambers that simulate the environment of the body, complete with oxygen and nutrients. After a few days of growth, something remarkable happens.
The tissue became functional, so these kidneys started to make a rudimentary urine. In the last step of this experiment, as the ultimate proof of principle, we were then able to take these kidneys from culture and transplant them in an animal model. So we took that final step to take the kidney out of the bioreactor and then treat it like a transplant organ, like a donor organ, and replace the native kidney in an animal with this engineered kidney.
But it's not always that easy.
And we had to figure out how much vacuum can be applied to the kidney in order to provide just the right amount of tissue gradient to deliver the cells, but not to damage the matrix. Of course, if more vacuum is applied, we had quite a few kidneys blow up in a jar.
Hiccups aside, laboratory-grown organs appear to be closer and closer to fulfilling their tremendous promise.
The reason why I'm most excited about this recent publication is because it shows the platform character of this technology. The technology can be applied to any tissue or any organ that can be perfused by its own vascular system. Ultimately, this is a very translational kind of research. It's very much focused on driving this all the way down to the bedside, getting this to the patient.
So this, you can go ahead and go to the next one. So in this model that we described here, it's about taking organs that we're not going to transplant, removing all the cells and repopulating. This is a very exciting project. MPA, Boston is working on the kidneys, Minnesota is working on the livers, and hopefully in the next year we can have a follow-up of the next
This is Luke Masella. He shouldn't be this healthy.
I was born with spina bifida, which is a birth defect. It's basically a hole in the spine where all the nerves develop. When I was 10, I got really sick, and they were trying to figure out what was going on. And I was in and out of the hospital every week, and they finally figured out that I was actually in kidney failure.
A faulty bladder was Luke's problem, caused by the spina bifida.
The bladder was sending fluid back up into my kidneys, which was making them not work correctly.
But Luke was given a remarkable treatment. At Wake Forest School of Medicine in America's North Carolina, researchers are growing artificial body parts. Luke was one of the first in the world to benefit.
They take a piece of your bladder out, they grow it in a lab for 2 months into a new bladder that's your own, and they put it back in.
Grow your own organs in the lab means no rejection problems and no waiting around for organ donors. It's called regenerative medicine, and it's an exciting future that awaits us all.
I see us getting to a point of having options available that actually stop disease processes, reverse disease processes, or offer people cures.
Simple organs, like bladders, are the easiest to grow. Cells were taken from Luke's original bladder, multiplied up, nutrients added, and that produced this pink solution.
And we then create a three-dimensional mold, and we place the cells on top of the mold.
The mold is in the shape of a bladder and is made from material that breaks down in the body.
We place the mold with the cells in an oven-like device. We cooked it, if you will, very much like baking a layer cake. And we then were able to take that organ out, and we were able to place it into patients.
And the team has cooked up more than bladders.
Another of the organs that we have targeted is the urethra, which is the channel that connects the bladder to the outside of the body. It is a very important organ, as you can imagine.
Some of Anthony's patients had had car accidents, damaging their urethras. So he decided to grow them new ones. They were like bladders, really, with a different geometry. Scaffolding was seeded with the patient's cells and nutrients, and then sewn into the shape of a urethra.
And we then were able to place those engineered urethras back into those patients.
To automate organ making, the researchers came up with an incredible method. Print them. They even started out with modified computer printers.
But instead of using ink, we use cells, and we print the cells with a gel-like material, one layer at a time, and we then allow the gel to get harder over time.
Nowadays, these bioprinters are purpose-built and much more sophisticated. Indeed, on the other side of the country, in San Diego, we visited startup company Organovo. They're planning to take bioprinting to market.
Very impressive looking labs. Brand new.
Brand new, been here for about 3 weeks. This is where the action happens. These are our tissue culture hoods. It keeps everything sterile, and we take the cells and build the 3D tissues within this space.
So it's kind of an organ growing lab in a way.
It is, absolutely.
This sophisticated robot is the bioprinter. It squeezes out 0.5 millimetre wide cylinders of bioink. The inks just clusters of human cells, remarkably holding themselves together in the correct shape, just with natural adhesion. 6 cylinders of cells are laid on each other to make a tubular blood vessel. In this cross-sectional diagram, the red circles represent the walls of the vessel.
This is a fully human blood vessel that we've created with the bioprinter here on the plate. And so you can see its three-dimensionality just as you turn the plate slowly.
Again, the cells have assumed their correct positions in the vessel by themselves. There's no scaffolding holding this together.
So how do the cells know where to go?
They're smarter than we are in a lot of ways. It's their inherent properties. I think it's it's leveraging the qualities that cells naturally have, which is to stick to each other. We are able to control the shape in which they do that, and then the printer builds the ultimate structure.
The next step is to give the cells nutrients and then put them in the incubator overnight. There, they'll continue to self-arrange and form a vessel.
After a night in the incubator and with a bit of cleaning, this is what you get. A replacement blood vessel made out of your cells.
This blood vessel is the width of a few human hairs. Back in North Carolina, they're developing another application for bioprinting, for wounds.
One of the strategies is to have a printing machine that not only prints but also scans. So basically the patient is first scanned, so the wound area gets a scan of the wound, and then we're able to go back with the printer and print the right layers of tissues right where they belong.
Now, for most organs, there's still a long way to go before they'll be ready for patients. But research is progressing on artificial kidneys, heart valves, large blood vessels, and skin. Here it's being slowly stretched out. They're even working on artificial ears and fingers.
Of course, fingers is still a long time away of us actually getting that into a patient. But the ear is simpler than a digit, and we're creating ears in the project we're doing right now with the military to provide these kinds of structures to our injured warriors.
Even muscles are up for replacement.
To create artificial muscle, we use the same strategies as we have used with other tissues, but we also exercise them. We put them in these small bioreactors, these exercise machines that actually stretch and compress the muscle structures so they build up strength over time before we implant them.
But the organs most in demand are kidneys and livers. And Anthony's team recently had a breakthrough. They developed miniature livers that functioned like human ones, in the lab at least. But artificial liver and kidney transplants are some way off because they're so complicated.
The kidneys have a very complex structure because it's a solid organ. And so unlike other structures like flat structures such as skin, which are the simplest, tubular structures like blood vessels or urethras, which are a second level of complexity, or even the bladders, which are a third level of complexity, the kidneys are a solid organ and have a fourth level of complexity. And therefore you have a lot more cell types, so it requires much more sophisticated methods for engineering.
Still, fixing up livers and kidneys may be closer than you think. We may be able to patch them.
If you take chronic kidney disease, for example, by the time a patient shows up at the doctor to say that I don't feel well, they are usually down to less than 10% of the function of that organ.
That says you don't need the whole organ to be replaced to feel well.
The tissue that is required to replace is actually only 10 to 20% to change the way that patient feels, change their quality of life, and really be effectively a cure for them.
Predicting the timing for any research is always difficult, but it's clear some pretty exciting developments are on their way. There'll be so many people like Luke who will benefit.
This is the second stage that we were going to present today. That is about bioengineering organs. And we have the last one that we're going to present.
With A&Es everywhere feeling the strain, particularly at this time of year. There's no doubt that organ transplants save lives, but waiting lists for compatible donors can never be short enough. So what if there were a way of producing compatible organs on demand? Bioprinting has traditionally meant printing biocompatible materials as a base for cells to grow. Though it may sound far-fetched, scientists have already managed to print a human ear and other tissues. Doctors take a scan of the organ to create a 3D blueprint. Cells are then taken from the patient, which are then placed in a culture to multiply. The cells are then painstakingly placed on the 3D printed scaffold, which is then incubated to produce a functioning organ. 3D bioprinting solutions opened its labs in September 2013 with the sole purpose of advancing tissue engineering. Supported by the Moscow Department of Healthcare and in vitro labs, the Skolkovo resident should soon have all the equipment necessary to manufacture organs. It's also working on a revolutionary bioprinting technique. The method still requires the 3D printed cell molds commonly used to store and grow various cell types, but crucially, it no longer requires the scaffold around which they are placed.
In 2014, Russia will have its first 3D bioprinter. This will far surpass any previous models, as it will be produced using nanotechnologies. Its speed and accuracy will far exceed that of any of the current models. And perhaps most importantly, it won't even be that expensive.
Traditional tissue engineering methods involve removing all the cells from a dead human or animal organ, leaving only the protein scaffold, which is then repopulated with stem cells and incubated. Mironov has taken this a step further and has come up with a method for printing an organ directly without the use of any organic or artificial scaffolds. It involves extracting stem cells from the patient's fat tissue, which are then mixed with a hydrogel and placed in 3D printed molds. These are then incubated to produce spheroids, which are the building blocks of organ printing. From here, you can pretty much print any organ you like.
We do not use animals or any synthetic polymers for support structures or scaffolds. We only use hydrogel.
The hydrogel is 99% water. It contains the spheroids, which are each made up of tens of thousands of cells. together making the bio-ink used to create organs. The printer lays down a layer of biopaper onto which the cell clusters are printed. Cells of the same type are naturally attracted to each other and combine to produce tissue. The process continues in this way, layer by layer. The biopaper eventually dissolves and the layers fuse and self-organize to produce a fully functioning organ.
The simplest tissues are those that don't have blood vessels, such as cartilage, skin, bones, and so on. The organs that we really need are kidneys, livers, hearts, and lungs, but that may only be possible in the distant future.
Although printed organs might not be here quite yet, doctors can already do some pretty impressive stuff. Stem cell therapy involves using new adult stem cells to regenerate damaged or diseased tissue. It may still be in its infancy, but doctors believe that the treatment has the potential to treat anything from spinal injuries and cancer to baldness and missing teeth. Heart disease is one of the biggest killers there is, with heart valve transplants running into tens of thousands in Russia every year alone. Thankfully, Penta-based Medinja's pyrolytic carbon heart valves are indistinguishable in terms of performance from the real thing, but provide the long life offered by artificial ones, giving many people a second chance. Bone implants are now commonplace, but that doesn't make them any less advanced. Porous nickel titanium alloy is a promising new material that's flexible when cold, but snaps back into its original shape at body temperature. But, just like soft tissue organs, bone implants also need to be accepted by the body, so they're given a special coating.
The surface coating should have the exact same composition as bone, so that the body doesn't reject the implant once it's inserted. So our task is to minimize the difference between the bone tissue and the implant. Ultra-thin calcium phosphate films do this perfectly.
Calcium and phosphate together make hydroxyapatite, which is a natural component of bone. The coating is applied by a process called physical vapor deposition, where calcium and phosphate are vaporized into a plasma, then condensed into a thin film onto the implant in this patented vacuum chamber. The whole procedure takes several hours, but the finely tuned ratios ensure the long-term success of the implant. The atoms gradually dissolve, stimulating bone growth around the implant, which results in a solid, natural bond.
As well as modifying bone implants, we have started researching ways to make ultra-thin coatings for coronary stents. As we all know, any malfunction of the cardiovascular system could be lethal. That is why searching for new ways to prolong the life of the patients is of utmost importance.
Stents are small mesh tubes that can be expanded to keep weak or narrow arteries open. Unfortunately, delicate arteries can be damaged during the implant operation or subsequent expansion. So, to avoid complications after the operation, the stents are coated in titanium nitride oxide, or TiNO for short. The super smooth coating helps avoid arterial damage and promotes healing, significantly reducing the risk of blood clots forming or the artery collapsing again later. The coating also remains intact as the mesh tube is expanded within the artery. Just like bone implants, the stent coatings are applied using the PVD process.
There is so-called early thrombosis and late thrombosis. The stents currently on the market guarantee successful treatment for older patients with early thrombosis. But there's increased risks of late thrombosis occurring even after several years. Our preliminary findings allow us to predict that we can avoid both early and late thrombosis.
Given all the medical breakthroughs we've already made, and with 3D printed ones coming in the not too distant future, hopefully we'll be able to start worrying less about our health.
Well, this was a little presentation to see what's happening right now at the forefront in creating organs, but I just want to leave a little past behind. We are already using here this morning about the application stem cells in clinical settings, not just for experimental clinical applications. There are other intermediate steps already happening There's a use of stem cell for chronic bowel disease, Crohn's disease, ulcerative colitis, and in transplant of the bowel to regenerate organs that have been injured. In the myocardial infarction area, there are already protocols about regenerating muscle. Why do we bring this? Why do we bring all this? We didn't come here to bring, we came here to share, to interact, and to say, let's try to see how can we do this together, and how can we develop programs like BioX program that we continue doing this work here in Ukraine for the patients of Ukraine. This is my last meeting, and I just want to say it's been an honor and pleasure to be here with you, and I hope that we can all dream together for a better healthcare in Ukraine. Thank you.